This whole week, we're going to look at a real-life situation that you can use quadratic functions to model, and that's gravity, gravitational pull. So this video is just going to be about the acceleration due to gravity. The word acceleration means how quickly your speed is changing. So the reason that you can't jump off of a building like this and be okay, whereas you could jump from like maybe the top of the door and be okay, is because the whole time that you're falling, gravity is speeding you up. Or if in the case of my friend Roger here, who's about to drop a ball off this thing that's 100 meters tall, the ball will be speeding up as it drops down. So it turns out that the acceleration due to gravity is a number that we know. It's about 9.8 meters per second each second. So that means for every second that an object is in free fall here on Earth, it's going about 9.8 meters per second faster. We're going to use the number -10 instead of, and why is it negative? That's a good question also. It's negative because gravity pulls downward towards the Earth. So gravity has a negative acceleration because it's pointing downward. But the acceleration due to gravity, we're going to use -10 meters per second each second. After falling, for 1 second, an object would be going 10 meters per second, which is about 22 miles an hour. It's like 22.3 miles per hour. Okay, and then if it falls for another second, so after 2 seconds, its speed is going so much faster. It's going 20 meters per second, or 45 miles an hour, and so on. And I'm not going to spend a lot of time doing this. Now, there's another thing to know, which is we're going to write a function for the ball here in just a moment, called f of t, or h of t rather. H of t equals, and I'm just going to I'm going to write it, and I'll explain it in a minute. It's -5 times t squared plus 100, because the ball starts at 100 meters high. So when the time is 0, the ball is 100 meters high. And after he drops it, the ball starts to speed up. And that's where the square comes in, because the h of t is really the height of the ball. But it's getting, the longer it falls, the faster it's going. Now, why is it -5 instead of -10? That's a good question, but it's something I'm going to have to just say, trust me, and you'll learn about it in calculus probably. But you use half of that gravitational constant here, because that's half of gravity. Okay, so now let's look at what that looks like and why we can use a quadratic to model this. So after 0 seconds, of course, the ball is 1 meter. And after 1 second, it would be -5 times 1 to the second power. So -5 times 1 squared plus 100, that's 95. So after 1 second, it would be 95 meters high. And it would also be going -10 meters per second. But after 2 seconds, that would be 2 squared is 4, and 4 times -5 is -20, so it would be at 80. After 2 seconds, it would be down here at 80 meters. And so you can see that it's starting to, this curve here, as it bends more, like the bendier it gets, the faster the ball is falling. At 3 seconds. Let's see, 3 squared is 9. Times 5 is -45, so I subtract that from 100, I get 55. After 3 seconds, it's made its way down to 55 meters, so it's getting even faster. And after 4 seconds, it would be 16 times 5 is 80, so it would be 100 minus 80, or 20 meters after 4 seconds. And then after 5 seconds, -100, it would be actually at -125 meters. -25 meters, because this would be 25 times 5 is -125, so it would be down here somewhere. I think it would be down about right there, but that means that really actually you can't get, unless there's a big hole in the ground, you can't do that. So that's the 0 right there. The 0, the 0 is somewhere between 4 and 5. It's roughly 4.5 seconds. At 4.5 seconds, it meets the 0, and you know what that actually means? It means that the ball hit the ground. Now, this is not like he threw it off the building, and the x-axis is not distance, it's time. It's the seconds that are going by. So after 1 second, the ball fell to this point. Then after 2 seconds, the ball fell to this point. and at 3 seconds it was here, and at 4 seconds it was here, and then around 4.5 seconds it landed on the ground, but the ball was just falling straight down the whole time. And when we're working with gravity, you have to understand that this does not represent the path of the ball. It represents, as time goes on, it represents the height of the ball. The last thing I wanted to show you is how do you actually find when the ball lands? Well, that means we would just set this function equal to 0, and we can solve it. And so what we would do is I'd subtract 100 from each side, and I would get negative 100 equals negative 5t squared. Divide both sides by negative 5, and I get 20 equals t squared. And then when I take the square root of 20, I get the time is actually 4.47 seconds, which is what we said was 5 seconds. Watch the next video on velocity before you do the assignment.